Over the weekend, I realized what I was talking about at the end of Friday's class, meaning when I'm drawing these model lines by not just the experimental data points, but if I want to make a smooth red curve to make a data model, I realized that wasn't totally clear, and it also wasn't completely correct. So I did the one parameter Margulies equation so that the line was nice and smooth, and I noticed that it didn't fit the data quite nearly as well as I thought it had before. The reason for that, again, is because if there's one parameter in the Margulies model, notice that the red curves are now symmetric. So it's the data, of course, is asymmetric, but remember, because the one parameter Margulies only has one parameter and it treats a system that is dilute in A the same as a system that is dilute in B, it has to have a symmetric look to it. So I did the first one already, and I'm going to walk you through how you would go about altering your Excel spreadsheet such that you get nice smooth red lines like this, and also a more accurate representation of what your model is actually looking like. So just as a preview, I mentioned that instead of just doing the data points, I'm making a range of X's and a range of Y's, and instead of the 20 data points that we have, I did 100 data points to go from X is equal to 0, adding by 0.01 every time. Same thing for Y. So really the only thing it entails is I added these two columns because these two columns were not here at the end of the day on Friday. And then I just had to update the cell references in the formulas and then update what data the model is actually plotting. So actually, I'm not sure what is going to happen for the two parameter case, but you can see this is what I was talking about on Friday. See like how there's some disjointedness looking like in the red lines here. We want to get that out of there because what I'm doing now is I'm actually plotting the same data points and then just connecting them with a smooth red line. And that's not actually what we want to do when we fit a model. So I'm going to do the same thing. Again, input or insert these two columns for X and Y. And then I just start with 0. And then I say equals 0 plus 0.01 every time. And I'm going to click and drag down until X is equal to 100 or 1. And I went way too far. So delete up to here. And same thing for Y. So I'm just going to say equals X. Okay. Yeah, I guess I didn't have to do two columns. I just realized that. You just have to have the cell reference correct. So I don't have to change anything about my model because we've already fit the activity coefficients. Right, so I don't have to update anything about this column or that column. I'm going to skip straight to my gammas. All right, so I'm going to click on the formula. And again, Excel is useful about highlighting for you. Sorry about that. I lost my train of thought. All I want to do is update my cell references such that instead of the experimental X's, I'm taking my hypothetical X's. I'm just going to click and drag this all the way over. So drag both of those, and then I'm going to double click this bottom right-hand square, and that's going to copy my formula all the way down. So don't worry about this funkiness that's going on. We'll fix that soon enough. I also need to, so this only works up until the column on the left goes. So I need to drag this all the way back down, actually. All the way, and then my activity coefficient equaling 1 at a pure component is a good sign. That tells me that I've done the adjustment correctly. I'm gonna have to do the same thing for my gamma 2. And this time when I double click, it should move. Oh no, it doesn't move all the way down. I gotta click and drag and highlight it all the way. And gamma 2 should of course be 1 at the other pure component. Same thing, updating the cell references. So I mentioned I don't have to do two separate X's and Y's since they're the same value, but just for sake of clarity, I'll keep it and update the bubble point pressure. All right. So I gotta drag this all the way down now. And then the final step is to highlight my data and then adjust it to what I want it to plot. So I want it to plot my y's. All right, and see, look already how nice and smooth that curve looks. There's no more disjointedness because I'm plotting many more points along this curve. So if you zoom in enough, it still will look disjointed, but from looking at the whole data, it looks pretty good. All right, and if I do the same thing for x, I should get the second one looking nicely as well. Interesting, still a little bit of error there. I wonder if there's, let me double check and make sure I didn't make a mistake here. Okay, after about a half hour's worth of troubleshooting, I finally have gotten the correct answer. And I thought about just deleting this video and starting over, but I think it's important to let you see the entire process of my thinking. So I realized what the problem was here is that my bubble point pressures were fine. And that's because bubble point is a function of x and gamma is also a function of x. However, for the dew point, I was using gamma, but I was relating gamma to the y. So actually, when I said you only needed one column here, that was incorrect. You do need two columns. The issue is that it's not a separate column for x and a separate column for y. So what I actually have to do here is solve for the y given my bubble point pressure. So once again, the gammas, the activity coefficients, are a function of x. They are not a function of y. And here, when I use the dew point pressure, or when I'm trying to calculate the dew point pressure, I'm using the gammas that are calculated based on y, and I cannot do that. So what I have to do is solve for my y by using, oh, I already put it in. So I'm solving Raoult's law again. So I'm just rearranging it to say that y is xa times vapor pressure times activity coefficient divided by total pressure. And total pressure is the bubble point pressure at equilibrium. So if I copy that formula all the way down, now I've got the y that corresponds to my x, and look at my fit of my Margulies model is actually very good. So we can talk about this in the next synchronous session. Again, this is a subtlety. This was a very subtle point, and I'm glad that I caught it because I think sometimes troubleshooting the nitty-gritty of what Excel is doing can be very challenging, and I know it is challenging for a lot of students. So hopefully this helps. I'm going to come up here and do the same thing and see what it does to my one parameter Margulies. So again, the issue here is that my dew point pressure is a function of my y, but the y cannot be used to do the gamma. So instead of this y, what I have to do is solve Raoult's law. So it's equals x times vapor pressure, and vapor pressure again was 24.36 kPa, or I forgot what the units are, kPa, times gamma, all divided by bubble point. And I know the bubble point pressures are correct. So equals, click and drag, and oh, that still looks pretty good. Interesting. Okay, so for this, yeah, I guess the bubble point was a little bit off up here, but it's not symmetric as I thought. The symmetry has to do with, or no, it is symmetric, I think. It's hard to tell. Maybe if I got rid of the circles, it would look more symmetric. Yeah, if I compare, let's bring these two side by side. So maybe I should label them a little bit better. All right, I've got one parameter Margulies on the left, two parameter Margulies on the right. Actually, you do see, especially like up in this region on the top of the bubble point curve, this is where my fit is really improving with the two parameter Margulies. So compare these 3 data points with these 3 data points, you can see the 2-parameter Margulies goes through them much better. So it's going to wrap up this video. I guess the next video, I wanted to start with this video because it's going to segue nicely into the next topic, which is it's nice to be able to use experimental data in order to fit my activity coefficients. But what if now we wanted to do the same PXY diagram, but for a different temperature? So instead of 303.15 Kelvin, what if we wanted to operate at a different temperature? Could we assume that the activity coefficients are going to be the same, or do they change somehow? And if they do change, how did they change? So that, again, that'll be the second video for today.